This
participation
call
of
is now
students.
being recorded.
So many what?
Like there are very few students in this class. I don't know why.
Maybe they'll come a bit later.
Let's see. So now we have about 8 students. So let's wait for 1 minute or two so that they can join back. Maybe there might be a question in the final term paper about plate girder. And at that time, they are going to wonder that how to solve this problem.
Yes, sir.
Yeah. Let me see how many students. So Amir is not back. So I will wait for 1 minute. Okay, I'm going to share the screen now. And okay, I hope you can see the screen. So we discussed that we have discussed about the flexure capacity of the plate girder. Okay, there are three limit states. We have to check every limit state, and then out of these three limit state, you have to select the minimum bending moment. Okay, you have to select the minimum bending moment. Okay, so this one and this one, whichever is giving the least value, so that would be your flexure capacity of the plate girder. So in order to demonstrate that, so we have an example. Just give me a moment, please. Assalamu alaikum, sir. जी सर. हाँ सर, मतलब पता नहीं था सर. सही है जी, ठीक शो जी, बिल्कुल ठीक है सर. सही है जी, ठीक है जी, ठीक है सर. नन को 14 तारीख थे ना सर. 14 दे जी, 14 दे नन को. जी जी सर. सर जमा 15-16. I'm sorry, I got a call from my senior. So there are some interviews in the commission, in the local government department. So we were discussing that whose turn is today to go for the to
No
act as
problem,
an.
sir.
So now we are going to see an example. Like it's a this example. You can see it is from the Sigway book, and it is problem basically in the exercise. Okay, basically you can consult chapter number 10. Okay, let me write it down. So where you can find details about plate girders in the Sigway book. So Sigway book, you can find chapter number 10. In chapter number 10, you can find all these details, okay, about these plate girders. And from the problems, okay, so I have picked this example from the problems of chapter number 10. Okay, so it says that you have to determine the, sorry, I will cross it here. So we have to determine this flexure capacity or the flexure strength of a welded shape. Welded shape means it's a plate girder. The flanges are 3 inch thick inches, and 26 inches is the web, and the web is about, I have to see that, okay, this dimension is 3 inches is, I think, these are the flanges. and this is I think 3 inches, and this is about 26 inches. Okay, so this is the for flange dimension, and for web I think web is about 48 inches. Okay, let me draw it. I'm sorry for my drawing. So let's assume that this is about 78 inches, and the thickness I have to see that what is the thickness. Thickness is about 0.5 inches. Okay, this is TW, this is 0.5 inches. Okay, now the first thing we have learned about the plate girder is that we have to check the classification. Okay, we have to check the classification of web. Is it compact, non-compact, or cylinder? Okay, and most probably this is going to be non-compact, or most probably we will have it in the cylinder case. Okay, so the web is cylinder. Okay, like we have studied that in plate girder, most of the times the webs are cylinder. Okay, now how we are going to check it? First thing is that we have to find this ratio. That ratio is this one. This is the height to thickness ratio of the web, and then you have to compare it with some equations. So I will go back, and what are those equations? I will highlight those equations. These are the equations. Okay, we have to compute this one, and then we have to compare it with this, that what is the classification of the web. Okay, so you can see that first you have to check the cylinderness or the classification shape for the web. Okay, you have to calculate this h by t. So this h by t is about 156. Now you have to compare this value. For example, say this is lambda. Okay, and this is the upper limit, which is, you can say that this is lambda r. And for lambda p, if we go back here, the lambda p is this one. Okay, so lambda p is 3.76 e by fy. Okay, now you calculate lambda, you compare it with lambda r and lambda p, and for sake of your convenience, I'm going to draw this figure here like this. So this is lambda p, and this is lambda r. Okay, and this lambda p and lambda r are given by this empirical equation, but on this axis you have this, I'm sorry, this ratio, and on this axis you have this bending moment. Okay, so you have calculated your h by t, and this value is 156. The lambda r value, this limit starts from 137.3. Now since this value is greater than lambda r, this falls in this range. Okay, this range we have a definite limit, and anything which falls beyond this limit, we classified that thing as cylinder. Okay, no, the one thing you should note down that your web is cylinder now. Okay, now you can see that this is the lambda r, it is 137, our h by t is 156. Now since it's saying that this ratio is greater than this one, so the web is cylinder. Okay, now as I told you that there are 3 limit state. The first limit state is tension flange yielding. For tension flange yielding, you have to use this equation, this Fy into S. Okay, this is I think in T. Yes. Now you have this one. Fy value is 50 ksi. Let me see in the statement. Yes, for A572, 50 grade steel, your Fy value is, okay. Now you have to use this equation. So you need S, and S is I by C. Okay. Now you need I, you need C. Okay. Now you can see that what is C? C will be, I think we have to see C value is about H by 2, which is the depth of web, plus thickness. Okay, this TF. So this you can plug it here, and you need this Ix value, okay, moment of inertia value. In order to get the moment of inertia for this wide flange section, you can use this equation, okay. So it's your job. Anybody is clear that everybody is clear how to calculate the moment of inertia for this section? And I'm leaving this to you, okay. This is a bit different formulation to calculate the moment of inertia. You can see that the first one is the BH cube by 12. Okay. The second is 2 times the area of the flange. Then this is D square. D square is, I think, this one. Now A. Okay. Like we know that moment of inertia is equal to, for rectangular section or whatever, you have this, you can use this square. So this is, you can say this is I bar at the centroid, okay. Then you have to add these values. So you have to relate this computation with this equation, and you can calculate I, okay. So this is 1 by 2, this is for flanges, okay, this is for flange, and sorry, this is for web, okay, this is for web, and this thing represents for flange, okay. For I shape, you can calculate the moment of inertia using this formulation, and C value is known, okay. So you can come up with this S value, which is elastic section modulus. Once you know the section modulus, which is like, for example, this is on the, this is tension and this is compression. So on the tension side, this is the section modulus of your section. Once you know that, you can use the first limit state, that is tension flange yielding, and you will just have to multiply it with the yield stress of the material. So you will get this value. Now the second limit state is the compression flange yielding, okay, remember. And for compression flange yielding, and the third limit state is the LTB. So it's saying that LTB, we will come to it later, okay, once we deal with the just give me a moment, sir. Assalamu alaikum, sir. जी जी हाँ 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 सॉरी सर माता पता ना हो सर जी सर जी सर जी सर जी सर ठीक है सर सही है सर सॉरी सर माता पता ना हो सर सही है ठीक 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 okay. Now the second is, sorry for the interruption. The second is the compression flange yielding. For compression flange yielding, you have to use this equation. If you remember this one, where is this one? This equation. Okay. And in this equation, the problem is that we need FCR. Okay. And this FCR, we have to see first, the flange is compact or is it non-compact or is it cylinder. So if it is compact, this FCR value will be equal to yield stress. Okay. So first you have to calculate the lambda. The lambda, you have to compare it with this LP value. The LP value is about, lambda p value is 9.1 inches and the lambda value is 4.33. So lambda is less than lambda p. So it means that FCR is equal to the yield stress of the material. And that yield stress is 50 KSI. So in the we have to use some moment reduction factor when we are evaluating the bending moment capacity or the bending strength of the compression flange. Okay, so we are good with this one, we are good with this one. We have to calculate RPG value. For this you need this AW value, and where you will find this AW value, this is you can find it by this equation. Okay, so it says that the upper limit on this equation is 10. Okay, what is 10? Let's see. Okay, we have to go to this. Yes. This limit is set by AISC. Okay. Okay. Now you can see that this equation. So in this equation, A is this one. So if you plug the A value here, this is 0.5, and the rest of variable, if they take their values in this equation, so you will have this value. Now this value you can plug in this equation, so you will get the moment capacity for the compression flange limit state. Okay, so you have this moment capacity that is 3.28 inch per kips, and you have this 3.25. So you have to compare it. And the third limit state we have studied is about the LTB. And in the statement, if you see that the member is simply supported, uniform loaded, and has a continuous lateral support. If you find this statement in your problem, it means that your LB is the LTB will be not a problem. Okay, so you do not have to check this one. So if you do not find this statement, then you have to check LTB as well. So now you have to compare this value with this value, and you have to select the least value. So in if you compare 3.28 and 3.25, so this is the least value. So the compression flange yielding is the controlling limit state. Now the capacity of your section of your plate girder will be this one. Okay, this value. Then you can multiply the phi value, and the phi value is about 9.9. Okay. So in this way, you can evaluate this plate girder flexure capacity. I will give you a few moments so you can think about it, and you can ask me questions if something is not clearer in this slide. Any question? Any question from your side?
Not so far, sir.
Okay. You can think over it. If you have any question, you can ask me. Like, is it say simple, or you find it difficult? Is it confusing?
Sir, up to compression is okay, but I want to understand what is R.
Which one? Which you are referring to?
Huh?
You want to understand what? Sorry, can you repeat it?
What is R?
R is here. This is a
RP.
strength reduction factor. See here. This one. This value.
Okay.
This the bending strength reduction factor.
It has only one formula.
Sorry?
It has one formula, right?
Yes, this formula. And it uses this AW value. And how you will get this AW value? Using this formulation.
Okay. What if it is exceed 1?
So then you have to use 1.
I got this one. Okay.
Is it clear now?
Yes, sir, it's clear.
Look, for the first, this is very simple. Only thing you need is this S. This S is I by C. You need C and you need I. Okay. For the second limit state, you need RPG. You need FCR. Okay. So this will come from the geometry of cross section. Okay. Is it clear?
Yes, sir.
Up to some extent. Okay.
Yeah.
I know it is very difficult to absorb these values at the first go. Okay.
Yes, sir. It took a while.
So think over it. Okay. I will go very slowly, gradually. First limit state, you have calculated the bending moment using this equation. Second, you have calculated the bending moment using this equation. Then you compared these two equations. Whichever is giving you the least value, so you will go for that value. You see here? First, you check the web. Okay, let me write it down here. I will add a new slide. This is important. Like, note it down with you, how to solve a problem. Okay, how to solve flexure strength or capacity of plate girder. First thing you have to check. Step 1. Check classification of web. Is it cylinder? Is it compact? Is it non-compact? Okay. And you can do this check by calculating this for your web. Okay. Then you have to compare it with two equations. Okay. First equation is this one. Second equation is this one. If this is representing the lambda p, this is representing lambda r, and this is your lambda. Okay. If this is less than, if lambda is less than lambda p or equal to, so your web will be compact. Okay. If lambda is greater than lambda p, so it will be either non-compact or cylinder. Second step is that you have to evaluate the flexure capacity based on tension, flange, yielding. You can do that using this SXT into FY. But in this, you need this. You need I, you need C. The second is compression, for that you have to use this RPG, FCR. You need this, but in order to calculate this, you need this. Once you calculate this one, you can calculate this one. You need this, you need FCR. In order to see FCR, you have to check the flange, whether it is compact, non-compact, or cylinder. If it is compact, FCR will be equal to FY. Okay? So then once you know you are done with the calculation, so you have to see that whichever is giving you the least value. Bending moment. So that will be your flux. And the one third limit state which I have not mentioned here is the LTB.
LTV, yes.
I know it is difficult. It is difficult to absorb it, but I have tried to summarize all the things on this slide. Any questions?
सर
Yes.
हम लोगों ने जो क्वेश्चन में मोमेंट ऑफ इनर्शिया का फार्मूला यूज किया, उसकी क्या स्पेसिफिक रीजन है? मतलब हमने PH3/12 स्पेसिफिकली क्यों नहीं किया? +2a हमने क्यों किया सर?
I don't know. We have to check that formula. Okay. Like you are saying that, okay, like this you can evaluate as by I by BH cube by 12. Okay. And for this is your I1, this is your I2, this should be BH cube by 12, and this should be BH cube by 12. Okay. This is I3 BH cube by 12. Basically, first we need this one, which is at the bend at the neutral axis. And simply it has neglected the bending moment of this portion and this portion. And straight away it just used the bending moment of inertia of this one. Okay? Only the web. And in the AD square term, they use the area of flanges, and then they use the C value, the D value. And this is very strange. This was very strange for me as well. But I'm trying to figure it out. Still, I'm trying to figure it out, honestly.
Sir, actually, I have watched a video for this.
Sorry?
I have watched a video for this, but the justification that they have said, this figure we have 3 centroid. So in order to have a common centroid or moment of inertia, we got to use this formula.
So where did you find this information?
Actually, it's a YouTube series.
YouTube series, okay. Can you share the link in the classroom, please?
Okay, sure, sir.
Can you share the link to that video in the classroom, please?
Yes, sir.
So it will be easier for us, okay, including me, okay, honestly.
Okay, no problem, sir.
So can you do it right now?
Okay, let me just search it now.
Yes, we are waiting.
Okay, sure.
Once you are done, please let me know.
Okay, sir. I'm searching.
Are you done?
No, sir. Just because I watched it before a few weeks ago, so it took a while.
सर एक वीडियो मैंने मेरे सामने भी आई है लेकिन मैंने उसे पूरा नहीं देखा, लेकिन उसने यही फार्मूला यूज किया हुआ है।
तो आपके पास वो वीडियो है?
जी सर।
तो वो लिंक शेयर करें ना जरा क्लासरूम में आप।
मैं करता हूँ सर।
ओके।
सर ये वीडियो मैंने पूरी नहीं देखी लेकिन फार्मूला इसने यही यूज किया हुआ है।
ठीक है, ठीक है, you just share that, okay? Otherwise you can go for this, calculate the, you take this section, you calculate its centroid, you do the math and you calculate the moment of inertia for this section, and you can do it easily, okay? आपका जो you have a background of engineering mechanics, so it will be not very difficult. You remember in the composite beam we do calculate some values, okay, like moment of inertia of transform section. So try to apply that knowledge and you try come up and let me know that are you getting the same value or is it different? Okay. So has the video been shared on the classroom?
जी सर, मैंने मैसेज टेक्स्ट किया है इसी क्लास में, मतलब टेक्स्ट मैसेज किया।
No, do it in the classroom. Classroom.
ओके सर।
What's your name?
साथ सर, साथ।
अच्छा साथ इसको जरा शेयर करें उसमें क्लासरूम में शेयर कर दें काइंडली। अच्छा
जी सर।
Okay, now we will go through another problem that is based on the flexure. So we have to determine the flexure capacity of a shape. Okay, there is some misprinting here. So this is the flanges are 7 1/8 inches thick and 7 inches wide. The web is 3 1/8, I guess, or 3 3/8. We have to see. And the depth of the flange web is 60 inches. The member is simply supported and the span length is 40 feet. Lateral support is provided at the ends and mid. Now in this case, you have to check the LTB as well, okay? LTB needs to be checked as well, needs to be checked. Okay. So similar, first you have to check the classification of the web. So for that, you have to calculate this depth to thickness ratio, and then you have to compare it with lambda P and lambda R. So still it is greater than lambda R, it means your web is cylinder. And similarly, again, you have to, first you have to first limit state, this is tense, you see this tension, flange yielding. Tension flange yielding, you should calculate its capacity. You should evaluate. Now the next is the compression flange yielding. And for compression flange yielding, first you need to check the web compactness because FCR is needed. Okay. Now you have to check that you have the width is 12 inches. The thickness is 7/8 inches. Okay. The thickness of flange is 7 by 8 inches. And thickness of web is 3 by 8 inches. Okay. Now what you do, you have to check the flange compactness. Okay. Flange compactness. Okay. So once you see that, you will see that this value is 6 point this one, it is less than LB. It means your flange is compact. So what will be the value of FCR? What will be the value of FCR if the flange is compact?
Sir, equal to yield strength.
Yes. Now this is already there. So now you can use this one. Now you need RPG. RPG, you can calculate this reduction factor from here. Now in order to calculate this, you need AW. Okay. So you can, when you calculate this one, you check with the limit, then you plug that value, you calculate this one. Now you have two capacities. First is coming from here, the second is coming from here. So now in this case, you do not have this continuous stiffness, okay? So you have to check the LTB. For LTB, what you are going to do is that you need brace length. You have to calculate the brace length. So in the statement, you can see the lateral support or stiffeners are provided at the ends and the mid span. Span is 40 feet. And stiffeners are provided at the mid. So the LB will be the brace, unbraced length will be this one. There are 3 points. This one, this one, this one. So this hole is 40. In order to calculate this LB value, so you can divide the whole length and you will get this LB value. Now the LB value is 20 feet. Now you have to compare it with LP and LR. LP is 6.566. Now, Saad?
Ji sir, ji sir.
Now you have to calculate this RT value for this problem, okay? This is your assignment.
Okay,
and
sir.
share it in the classroom. You will get some extra credit, okay, for this.
Okay, sir.
Yes, you will definitely get it, okay? Oh, somebody can do this RT value and post it in the class to help the rest of the students. So they will get the extra credit, but if Saab does it first, so he will get the credits. Okay, Saab?
Okay, sir, inshallah.
Okay, do message me your class number as well, okay?
Okay, sir.
Now, LR is 22 feet. So the LB value is in between LP and LR. It means that it is not compact, okay? This is non-compact section. And in the non-compact section, what do you think? Will it be subjected to elastic lateral buckling or inelastic lateral buckling? This is total inelastic, like there is no buckling if the section is compact. Over here, this is LP, this is LR, this is non-compact section. It means inelastic buckling. The bending moment is greater than My and it is less than, let me write it here, M will be greater than My, but it is less than MP. So this section is not going to reach MP. It is going to fail by inelastic buckling if the value is between LB and LR. So for this case, you need FCR. FCR you can calculate, okay? And for this, you have to calculate the CB value. Okay, this is a simply supported beam. and it is loaded with where is that, uniformly loaded. So if this is the case, so what will be the bending moment? Somewhat like this. And for this, you have to calculate the CB value. And then you have to use it here. Or you can use the textbook, or you can go to the manual. If you remember 3.2, I think this table in the AISC manual. So now you have this capacity, which is, where is the capacity? This one. This one. You have this one. Whichever is the least, that will be the controlling one, okay? So this is the least one, so this will be the capacity, flexure capacity of your plate girder. Saad?
जी sir.
Now what you have to do is that you have to also add or hand calculated CV values in this problem, okay, in the classroom, okay?
Okay sir.
So that people, when they are solving some problem in the final exam, so they have some, they understand what they are doing.
Okay sir, inshallah.
Okay, now still, okay, now there is another example. So this is, I think, from the chat, this is 10.1, I guess, in the Segway book, okay? Now there is a 80 feet long plate girder fabricated from, I don't know, there is misprinting in the book as well. So you can see it, the steel is this one, the loading consists of service this, live this. So stiffeners are placed at each end, and 4 feet, 16 feet, this one, this is the distribution. One stiffener is placed as middle, determine whether the flexure strength is adequate or it is not adequate. So you can see here, stiffeners, these are the stiffeners. So this is the situation, the loading situation scenario. So what you do the web classification, and obviously it is going to be cylinder. Let's see. This is 50 divided by 0.25 is, I think, 150. How much? Let me see. $150. No, sorry, 50. This is 200. This value is 200. This is obviously greater than this value. So your web will be cylinder. Okay. Now if still you have to use the same equation, this I have very proximate equation, but we have to see, we have to confirm it. And Saad is going to add the aid in the classroom, okay? And he will get extra credits. Oh, sorry. Got it. Okay, now you have to tension flange, the same formulation.
How much credit he will have?
Maybe 2 marks, 3 marks extra.
Good then.
Are they enough?
Sir, they are more than enough.
Okay. The second is the compression flange limit state. This is the second limit state, okay? The reason I'm repeating these questions, because you should get familiar with these methodology, okay? So you have to check the flange compactness, okay? If it is less than LP, so FCR will be equal to FY. For this, you need AW. You can calculate AW from here. Similarly, you can go with this and you can calculate this value. This value is something 2.79 10 raised to the power 5. Now you have to see the, okay, it has not considered LTB, but it should have considered it. So LTB is not there, but you should include it. Okay, you should include LTB in this problem. If this problem appears, or any problem similar to this one appears in the exam. Okay, is it clear now? LTB should be included. Okay, Ahmad.
Yes, I'm with you.
Okay, Saad, Amir.
Yes, sir.
Okay, LTB is not there. Okay, you should include LTB. Okay.
Okay, sir.
You have to check the brace length first. LB unbraced length will be this one. I think 12 feet. Now you have to calculate the LP and LR. LP, how you can calculate LP? You can use this information. Okay, LP, LR. Then you have to compare it with this unbraced length. Okay. Now the next is the shear design. What is the time? 10:25. Should we include shear design?
I guess that it's enough so far because you have a class after a few minutes.
Okay. For shear design, okay, let me, okay. Yes. Now, how to carry out the shear design? Okay, these are the steps. The first step is the compute the aspect ratio. What is A? A is the spacing of the stiffness. Okay, this is A. What is H? H is the depth of flange. First, you have to calculate this ratio. Then you have to check the slenderness of web. Then you have to calculate this plate bend. What is this KV and CV values? Okay. Now there are two situations. Okay. Now shear strength in plate girders can be determined in two manners. First manner is that it is a sum of shear stress before the buckling and after the buckling. Okay, if after the buckling there is a contribution, so then you have to use this equation. If there is no contribution post buckling, then you have to use this equation. And this post buckling is permitted, and it is indicated by this tension field action, which is generated in the intermediate panels. It is not generated in the end. And so what is this? Tension field. You have to check that. Okay, so this is how you're gonna proceed. Like, first you have to check the A by H value, aspect ratio. It is for if this KV value is plate buckling coefficient. This is, you can find by this equation. But if the aspect ratio is greater than 3, okay, then this value will be 5. This value will be still 5 if A by H value is greater than this factor. If your girder is unstiffened, okay, unstiffened webs, okay, then you have to use, if this situation is there, then you can use KV value equal to 5. Okay, so for CV value, if your aspect ratio is satisfying this equation, CV value will be 1. If aspect ratio is in between these two equations, then this will be the CV value. If the aspect ratio is greater than this one, then you have to use this equation to calculate the CV value. Okay. You need KV, you need CV. Okay. Now let's go through this statement. How much time is left? Let me see. Okay, we still have time. The shear strength of plate girder is a function of depth to thickness ratio of the web and the spacing of intermediate stiffeners that may be present. It means the shear strength is a function of depth to thickness of webs, and it is also and the spacing of the intermediate stiffeners, which is A by H. Shear strength of plate girder is a function of these two things. Okay, so if you have this different aspect ratio is varying, you have different cases, the KV value and the CV value will be changing. The shear capacity in the plate girder has two components: strength before the buckling and post buckling strength. The post buckling strength relies on a thing or phenomena that is called tension field action, which is produced possible by the presence of the stiffeners. If stiffeners are not present or are spaced far apart, tension field action will not be possible. If we have tension field action in our equation or in our plate girder, then you have to use this equation in order to evaluate the if tension field action is possible, then shear strength will be of two components. Okay, see, this uses CV value. Okay, so if the tension field is not there, okay, then you have to use this equation. If tension field action is not possible, then you will use this equation. I hope I got it right. Let me see. The first term in equation give the shear, when the second term give pose. If there is no tension, yes, okay. I'm sorry. So you have two scenarios. You have tension field, then use this equation. If there is no tension field, use this equation. Okay. Now compute the aspect ratio and the slenderness ratio. Compute KV and CV. Determine whether the tension field action can be used or is it possible. Then calculate the shear strength using this equation. If the tension field action is not permitted, then use this equation. Okay. So there is a problem. Okay. Compute the nominal shear strength of end panel. In the end panel, if I remember, tension field is not permitted. Okay. If the first immediate stiffener is placed 70 inches from support, we will see. Okay. First thing, you have to calculate the web slenderness classification. Okay. If you calculate the depth to thickness, you calculate the aspect ratio. Aspect ratio should be less than 1. Okay. If it is less than 1, so tension field is permitted. Okay. So this is very confusing. So I will go to the book. Okay. And I will show you where to find the relevant, how to check the tension field is permitted or it is not permitted. Let me see. Yes. Yes, you have to, okay. So it's saying that you see this, there are indicated by A, B, C, D, okay. The tension field cannot be used in the following cases. If it is in the end panels, if A aspect ratio is greater than 3, and this aspect ratio should be greater than this value as well, or this situation, or this situation. So you have to check all four, okay. If I take a snapshot from here and I paste it there, okay. This one, oh, this was the one. Yes, should bring it here. Yes. Now this is doing this. A by H value is less than 3. So it is not greater than 3. It means there is a tension field action. Okay. Now the tension field action is there because A by H value is not greater than 3. And the second is this one, 260 divided by H thickness of web. This value should be greater than A by H. So this value is 3.75. Whether and this value A by H is not greater than this value. You see, A by H is 1. This is 3.7. So it means that tension field exists. Okay. And for that, you have to use the modified equation. Okay. No, I got it wrong. Okay. So you have to calculate KV. Then, yes, the first thing we have missed, I'm sorry. In the end panels, tension field cannot be developed. So you can see that in the tension field equation has not been used. Okay. Because you see, this is saying that this is an end panel. In end panel, tension field is not permitted or it cannot be developed. So you use this equation. For the second equation, you see that this is an interior panel now. In an interior panel, shear tension field is possible. And the spacing of stiffener is given. This spacing of stiffener is representing the A value. A is 200 in this case. Now you are going to check. A by aspect ratio is less than 3. Tension field is possible. Okay, if one of the criteria is satisfied, so you have to check all. If one of them is satisfied, it means that tension field is present or it is not present. You can decide about it. Now in this case, only this area is satisfied. That aspect ratio is less than 3. If it was greater than 3, there was no tension field. Okay. So for this, you have to use this modified equation. Okay. Okay. And you calculate CV and you just plug in the values and you can calculate the shear. Okay. So what is the third case? What is the nominal? If no intermediate, if there are no stiffeners, A value will be very high. And obviously A by H value aspect ratio will be greater than 3. Accordingly, you will use this equation. Okay. I hope it is somewhat clear to you to see the recording. Okay. So if you have any question, you can post it in the classroom. I will try to answer your queries. Okay. I went a bit faster. Okay, with fast pace in the shear, but I hope it is somewhat clear to you now. Is it somewhat clear to you? Or you guys are all sleeping?
Yes, yeah, your explanation is clear, sir.
Okay, just go through it and expect 1 or 2 problems in the paper from plate girders. Okay.
Okay, inshallah, sir. Thank you so much, sir.
Okay, where is the classroom? So I'm going to stop the recording.